Okay, right, we've had all the introductions. Where do we start? We get into the deep end with parallel processing. Fascinating that we had two contributions on the same topic, parallel processing, which I hope are very complementary because they attack the problem in different ways. Parallel processing has been a promise for many years. For years I've been telling people, why do you have to put up with this pain of variables that aren't really variables? Well, it's because declarative programming is a really good idea. Functional programming is a good idea. Not only does it remove the bugs in your program, it also gives the processor a lot more scope to do optimization, and one of the scopes it gives is to, for example, to execute things in parallel. And after 10 years, that was beginning to feel a bit like an empty promise. When will we actually realize some of this stuff? And decided to start doing something about it. Particularly when you get a new laptop and you find it's got 4 processors on it, and you look at the little meters running on it, and only one of them is doing something. You think there must be a better way of using all this wonderful power that the hardware vendors are giving us nowadays. So Moore's law still applies. We're still getting more and more processor power every year, but increasingly it's being delivered by not giving us faster processors, but by giving us more processors, and more processors on a chip, and that depends on software taking advantage of the new architecture. There's an obvious fit with a language like XSLT, with a declarative programming language. It's been known for years that you ought to be able to optimize declarative languages to do parallel processing. Not just for improved throughput, which in a sense we've been able to do for years. If you're running a web service, then you can run lots of transformations at the same time using your processors, but also for improved latency, which means making one transformation run faster. So there's an obvious fit between the need for parallel processing and writing your applications in a declarative language like XSLT. So let's look at how it can actually work. How many times have we told people on XSL list and Stack Overflow that for each is not a loop? How many times have people asked, how can I exit from a loop? Or how can I assign a variable in one iteration through a loop and then use that variable in the next iteration through a loop? Answer is you can't, because it's not a loop. XSL for each is a functional mapping. It's the classic mapping operator that you get in functional programming, where you apply the same function to all the items in a sequence. It's disguised as a loop, but it's not a loop. What it does is it very subtly disguises the body of the for each loop is the function. It doesn't look like a function, but it is a function. It's a function of the context item, so it takes an implicit parameter, which is the context item, and it applies the function, which is the instructions in the body of the for each loop, to each item in the sequence to produce one or more items in the output. And those, in principle, can be executed in any order or in parallel, as we've told people so many times. Well, it's now a reality. They can actually be executed in parallel, and I'll come on to that in due time. So first of all, let's remind ourselves that ever since we started, and this is not unique to XSLT, there's been what I call trivial multithreading available. And by trivial multithreading, I mean that you can compile your source style sheet into some kind of executable form, which might be real compiled code. I don't think anyone compiles to machine code, but compiling to some intermediate form, which might be bytecode, or it might be an expression tree that you interpret, or whatever. But in an abstract sense, a compiled style sheet. And then you can execute that compiled style sheet on multiple input streams in parallel to do several independent transformations inputs to outputs. What do you achieve by doing that? You clearly achieve amortization of the cost of compiling the style sheet, compile once and execute many times, and you can achieve unlimited, in inverted commas, throughput when you're running a typical, your typical sort of publishing website where you're doing transformations on demand for each input request. You know, some of the academic online publishing services are running sort of 20 or 30 requests per second, and each of those triggers at least one transformation, possibly multiple transformations. In one that I was familiar with, it was triggering about 10 transformations, and those can all execute in parallel and deliver the throughput that you need to run that kind of service. I mentioned that as an example of multi-threading because it already introduces us to some of the problems that you can get with multi-threading. And there are two problems that you have to tackle to make that work. One is the problem of contention, and the other problem is the problem of bugs. Now, you'll hear people talk about contention, and you know, it's a respectable computer science thing to talk about how to eliminate the effects of synchronization and the delays that you get through people queuing for shared resources. You won't hear many people talking about bugs, because bugs shouldn't exist in theory, should they? And if you're an academic computer scientist, then you don't like to admit that bugs actually exist. But I'm not an academic computer scientist, I'm an engineer. And you have to face the reality that designing a bit of software with multi-threading in it, shipping a bit of software with multi-threading in it, is a bit like shipping a high-performance motorcycle. You know that some of your customers are going to kill themselves. It's intrinsically dangerous. We are not going, if we're shipping multi-threading, then we are not going for maximum safety and seat belts and inflatable airbags. We are going for maximum speed, and some people will hit the crash barrier. So that's something we have to bear in mind, that when we're doing this, we need a whole new range of techniques to make sure that the stuff is reliable. Contention arises when you have shared resources. Contention has historically been a bit of a problem with Saxon. And it's particularly a problem because of the way Saxon runs its name pool. What Saxon does is it compiles the style sheet and it compiles the source document, and both of them are done in the context of a name pool. And the name pool is a mapping from names to integers. And the whole idea is that when you search a source document, the source document contains those integers, and the style sheet contains those integers, and you can tell when you do a search for all the descendant XYZ elements, then that's an integer comparison, saying you're just looking for nodes in the tree that contain a specific integer value. And it's an extremely fast loop. I mean, I looked at the search of the descendant axis when you're searching the descendant axis for a specific element name and searching the whole document, and it's doing the inner loop for that is about 6 Java bytecode instructions. And those instructions essentially do an integer comparison. So that is lightning fast. I mean, I had someone published an independent paper on performance and said Saxon is not doing a linear search. Saxon is using indexing. And they were quite wrong. Saxon is doing a linear search, but the inner loop of that search is so fast that they couldn't measure it. And so they concluded we must be doing indexing. But it's not. And searching a document for a particular element name is so much faster than parsing the document that you just don't notice the cost. And that's because of the name pool. But the downside is that the name pool does cause contention. Why does it cause contention? Essentially because every time you allocate names in that name pool, you have to synchronize on it. You're allocating names when you compile a source document, because every name you're having to see, is it already in the name pool? If so, allocate the name. If so, use that integer. Otherwise, allocate a new integer. And you're getting locks on it when you compile a style sheet, because there the names in the path expressions also have to be mapped to the same integers. In the past, we were actually using the name pool quite a bit more. For example, the name pool would be used on output documents. It was used in the serialization pipeline. So, for example, the HTML indenter, which has to say, you know, what kind of element is this? Can I indent this kind of element? That was doing integer comparisons to test the names and see whether to indent them or not. So the name pool was being used not just for input documents, but for output documents. Well, answer is, we had to reduce the amount of contention, so we got rid of it from part of the pipeline. And gradually over the years, we've been reducing the use of that shared contentious resource to the place where it really adds value. But still, as we move more to higher numbers of threads, you can still spot that the throughput you get goes down and the amount of contention increases on that resource. So there's an engineering trade-off we have to make there. That says we probably need a technique that optimizes more for high throughput concurrent workloads, even at the cost of making single transformations run a little bit slower. It needn't necessarily be much slower. There's ideas for doing that based on just getting an indirection between the integers used in the style sheet and the integers used in the document. As my professor at university used to say, there's no problem in computer science that can't be solved by adding another layer of indirection. You know, a fractional increase in that loop from 6 instructions to 9 instructions might solve those contention problems, and that's a decision we have to make. That contention exists simply in that world of trivial multi-threading, but it increases the more you try and do multi-threading within individual transformations, which is something we have to look at. So contention and bugs, those are the two issues. Bugs, you know, I hate to admit it, Saxon has bugs. And we're very open about it. You know, I've always had a policy that says we publish all the information about all the bugs. You can see what they are, and we encourage people to report them. We welcome with open arms every bug report. The more we get, the happier we are, because we know the bugs are there, and we hate to think that people aren't telling us about them. And bugs in concurrent workloads are the worst to solve. They are dreadful to solve. Java doesn't help us much. The design of Java doesn't help us much prevent those bugs. The kind of type safety that we're used to with modern programming languages, it helps us to avoid all sorts of bugs that we used to write, you know, array-bound checking and type checking and all those sort of things. Modern languages help us to avoid those bugs and get them out. But concurrency bugs, no, you just have to get the code right. There are no tools in the world that help with that problem. And when all the testing in the world doesn't help with the problem all that much either, because some of these bugs only happen once a year. They're probabilistic. You can't be sure that you've tested all the bugs out. And when they do occur, we've got one customer at the moment who's been battling with a concurrency bug for about 6 months. It brings their system down about once every 6 weeks. They're working hard with us to capture the diagnostics, but every 6 weeks this bug comes up and brings their system down. And it's you know, it's hard work for the customer and it's hard work for us to solve that problem. And I've told them to get rid of the multi-threading in their application, and they said, no, we can't do that. It would run 4 times slower if we did. So, you know, real engineering trade-offs and problems that you've got to tackle in that area. More recently in Saxon, we've been introducing multi-threading within a single transformation. There's no clock in this room, is there? So this is not just about improving the throughput of a workload as to how many transformations you can run per second, but it's actually doing multi-threading within a single transformation. I'll talk a little bit about each of the areas where we're doing multi-threading in a moment. So first of all, a very simple example of where one can use multi-threading. I think in the 2.0 specs, there was a function introduced called collection. It was introduced for database people who want to work on collections of documents in a database, but it's actually very handy if you're processing directories of documents in a file store as well. And in the Saxon context, that's how we're using it. If you want to do bulk processing of a lot of documents in a directory structure, you can use the collection function to process them all. And in the most recent releases, the collection function is multi-threaded, which just means that we've got one process that gathers all the URIs in your directory structure, and then it feeds those documents to a number of threads. Each document is parsed in a separate thread. Well, there's a pool of threads that you don't have one thread per document, but you have a pool that you use. The parsing happens in parallel. There's then a sequence of trees delivered as the result of the parsing, and then the collection function collects those trees together in sequence. There's some interesting design questions as to whether we should try and retain the order of the result. Some people like to think that when you read the files in a directory, then you're going to get them in a predictable order. The spec doesn't say that the order is predictable, but if you run the same thing twice and the results come in a different order, some people get a bit upset. So there's a sort of usability versus performance trade-off there. Should we try and respect order or not? And we've oscillated a little bit on that one. But depending entirely on your workload, multi-threading the collection function can halve the execution time of that kind of workload. Because a lot of transformations are dominated by parsing time, and therefore doing the parsing in parallel can have a big impact. On the output side, that's transformations that are reading lots of documents. There are other transformations that are writing lots of documents. And this gets rather more interesting because these days when you do an XSL result document to start outputting a new document, we're starting a new thread to execute the XSL result document instruction. So in principle, every result document you output is output in a new instruction. And here you're actually executing different instructions in the style sheet in parallel with each other. So there we're totally dependent on the fact that the language is free of side effects, that you're not updating global variables, that you're not writing to shared resources, that each instruction is a functional unit and has a well-defined functional behavior without side effects, so that we can execute the instructions inside that result document instruction in parallel with the instructions outside it. If you're generating 1,000 output documents, this is typical of a sort of batch publishing kind of workload, then a new thread for each one, again allocated from a pool whose size you can control with configuration parameters. What's the impact of that? Well, we've seen, again, it can improve the elapsed time for that kind of batch publishing process by a factor of 3. It depends what you're doing. If you're just doing simple splitting of a source document, then it sometimes makes no impact at all, because it makes more impact if you're doing a significant amount of work to generate each result document. There's a new thing in XSLT 3 called XSL Merge. This is for streaming use cases. Classic use cases where you want to merge a collection of log files and they're all sorted in date-time order. So you want to, it's back to magnetic tape processing, isn't it, where you read you sort and merge using your magnetic tapes. But you don't need to read each of those documents into memory in order to merge them and produce one output document. You can merge the records incrementally from the different files if you know they're sorted in the same order according to a compatible sort key. And the XSL merge implementation in Saxon is multi-threaded. What's happening is, again, as with collection function, the XSL merge is generating a set of URIs. Each of those URIs is going to a separate parser. We're using a push parser. You might think it was more sensible to use a pull parser, but we get more reuse of Saxon internals if we use a push parser. So my little cartoon men are pushing and pulling here. The parser is pushing to a shared buffer. There's another guy pulling from that buffer, and the merge process then is pulling elements in turn from each of those shared buffers. And the maximum memory that you need is just as much as you need for the shared buffers to enable the threads to operate with minimum contention on the buffers. So that works quite nicely. Not many people are using XSL merge. It's a rather specialized requirement. But if that is your requirement, then it's a very handy tool indeed for solving it. And then finally, and perhaps the sort of gold standard of this, is, as I mentioned at the beginning, multi-threading for each. And this is different because we don't do it automatically. We only do it if the user asks for it. Because we simply don't know when it's a good idea to do it. In extreme circumstances, I ran one test just to do a sort of edge case test where I did a for each in string to code points. So I was taking a large string and splitting it into characters, and I did that in a multi-threaded way. So each character was being processed in a separate thread, and it increased the execution time from 10 milliseconds to about a minute. But it worked. But that's a case, that's to sort of illustrate the fact that this can seriously damage your performance if you use it inappropriately. Where it works well is where you know that processing each item is going to take quite a long time. So the longer the elapsed time for the processing work of each item, the more benefit that you will get from multi-threading for each. And so you switch that on explicitly with a Saxon extension attribute. And I've got feedback from users who are getting a fourfold performance improvement by using this and by tuning where they use it to optimize their particular workload. But we don't know how to automate that at all. So overall, what are the performance benefits? You can expect to get a 2 to 3 times speed up. Obviously, depends on the number of processors you've got, depends on your workload, depends on any number of factors. But that's the kind of order of magnitude you can look for. And as I've said, some aspects you can do automatically. We can make the decisions in Saxon. All you do is install Enterprise Edition and you get multi-threading automatically unless you switch it off. Or there are cases where you can select it manually. We haven't exhausted all the possibilities. Some things we can consider that we don't do yet are, for example, multi-threaded sorting. Sorting happens either because you request sorting with an XSL sort instruction, or it happens because there are a lot of XPath things where the semantics say the results have to be sorted into document order. And so both kinds of sorting have the potential to be done in parallel. Perhaps we can even just pick up an off-the-shelf parallel sort implementation to do that. The scope for pipeline processing to be multi-threaded. So both micro-pipelining within a style sheet and macro-pipelining of multiple style sheets connected together using XProc or using the Java APIs or whatever. So if you're running a sequence of transformations, there's no reason why one transformation shouldn't run in parallel with the others in the pipeline, if you've got enough memory, of course. And then one thing we found in measurement is that Saxon compilation takes a long time. There's actually a potential for us to use multi-threading during the compilation phase of a style sheet. Most of the compilation work of optimizing a template is independent of the optimization of other templates. There's no reason they shouldn't be done in parallel. So that's it. Do we have time for questions?
One, two. Okay. So we have plenty of time for questions. So any questions?
George is waving his
Seems
hand
like
vigorously.
George is trying to say something.
Thank you, Michael. While you're presenting the XSLT for each example with the character performance that increased from 10 milliseconds to 1 minute, I was thinking whether it will be an interesting idea to dynamically decide whether you will use threads. Like, you know, running the first execution on the first item,
Yep.
and then analyzing the time spent on that, and if it's a long time, then decide, you know, maybe I will allocate 3 threads.
Yeah, I'm sure there's scope for that. Yes, perhaps we should get a PhD student to spend a year with us and implement such a thing. I'm sure it would be an excellent topic for research. Quite tricky, and one of the drawbacks with making decisions on the fly is that doing it in a way that doesn't add to the overhead. But yes, there's a lot of scope for dynamic optimization in this and a lot of other areas in Saxon, and we don't do much currently.
Thank you.
Any other question? Oh. Ooh, yeah.
I'm interested in, Phil Fearon, Delta XML. I'm interested in diagnostics when we're performing parallel processing, and specifically how instructions like XSL message and embedded functions like the trace function would operate.
Yep. It's a disaster, basically. I think if you're doing debugging, if you're debugging your logic, then you pretty well have to switch multi-threading off. And we were discussing this with George yesterday. If you're diagnosing your code and you're using a debugger, then you want to understand the way your code executes, which probably means you want to switch a lot of optimization off. The problem if you switch all that optimization off is if you're not just if the problem in your code is that you're calling a Java extension function with side effects, then eliminating the optimization is also going to eliminate the bug. So you're into a Heisenberg situation where if you switch the debugger on, then the bug goes away. So you've got that kind of challenge. But if you've written regular XSLT code and you want to debug your XSLT code, then and you want to use a traditional step-by-step debugging sort of approach, then you need to disable all this stuff.
Okay, thank you.
Hi. So I was interested in where you're trying to reduce the contention on the name pool.
Yeah.
And I wondered if you'd looked at using any lock-free data structures.
Any
lock-free data structures?
No, I haven't. And that's an interesting question because, I mean, it really means the semantics of Java in terms of what are atomic operations and what aren't get very complex and interesting. And it is probably something that we need to look at more carefully. Whether we can do that in a way that's completely lock-free, I don't know. It might be possible. It might well be worth looking at. Thanks for the suggestion.
Cool, thanks.
Hi, it's Alex Malowski. I have a simple question, maybe, about you've got this 2 to 3 times speed up, but there's always a space-time trade-off. So what is the consequence on sort of the memory consumption and so forth?
In some cases, it'll increase memory. I mean, for example, if you're using the collection function, then only having one document in memory at a time is going to need less memory than if you've got, 8 documents in memory at a time. So yes, it can lead to an increased use of memory. Other cases, like the XSL merge, what we're doing is enabling streaming and enabling a reduction in memory use. So it's certainly, yes, it doesn't have zero impact on memory use, so you're quite right there. Has to be considered.
Okay, any other question? Last one for me. You mentioned that Java is not the right tool to do that, but did you try to consider using other JVM-based language?
I don't think any language really solves this problem, from what I've seen. Languages offer increasingly rich primitives for synchronization and so on, but I'm not aware of any programming environment that gives you, sort of type safety and static checking that your code is thread safe. I think it's still up to programmer discipline to get your code right. I mean, yes, and simply realistically, we've got a code base that's been growing for 15 years. Suddenly writing everything in Erlang is not an option. So,
Thank you.
okay, thanks.
Thank you very much.